one more time. So these two have been lined up, and so you can watch as it does the transition. You see a few of the stars down near the center in the optical, but once you see the infrared and go through all the dust, all the other young stars pop out. So the particular piece of work that I wanted to talk about here, we're actually trying to answer this question of, like, what is the net impact of all these outflows shredding the cloud from the inside? So here's just going back to the visible. Oh yeah, and then this is a close-up of this region, which is a famous one. And here you can see just a bit of reflection nebula around a hole. This jet is actually being launched from that star right there. And you can see that it's punched a hole. It's created a cavity that's coming out from the cloud. And there's another jet going in the opposite direction that's behind the cloud that we can't see. So that was one particular region. So this is zooming out. This is the same region again. So what would happen if we tried to look at an entire molecular cloud and see what the outflows are doing? So let's step back one more time. So this is that same image zoomed out. Now what I'm going to do is overlay data from a radio telescope. Now, the radio telescope will actually show us the gas and dust, the molecular cloud itself. So here it is lined up in the background. So the cloud, this is called the Perseus molecular cloud, actually stretches, this is several degrees across. This is about 3 or 4 degrees across. And so it's much, much wider than that one image. And I can fade that image out, and we see that there's a lot of regions in here which are actually forming stars. So what we did is we took that telescope, the Kitt Peak 4 meter, and we imaged this entire cloud looking for these shocks, these Herbig-Haro objects where the outflows are slamming into the cloud. And we wanted to ask the question, if I add all of them up from the entire cloud, can I figure out what their net effect on the cloud will be? So after imaging the whole cloud and cataloging all these objects, this is an overlay. So I've just taken the radio data, turned it grayscale, and then the red and the blue dots are these shocks from protostellar outflows. And what we did was we essentially measured how much area of the cloud is covered by these shocks. We had some estimates for essentially how much momentum is injected into the cloud by these outflows. And then we just did the sum, essentially, over the entire cloud. And what we were able to find is that the cloud, as a whole, is not going to get shredded by these outflows. And you can see that because once you get away from the bright, really active area that we've been talking about, the outflows and the young stars are much less common and more dispersed. But they extend a long way from their source region. So we find some of these outflows, there's an example down here where it's emerging from one part of the cloud and slamming into another one in order to answer Cliff's question from earlier. But if you zoom in and look at these dense regions, what you'll find out is the outflows have more than enough momentum that's being pushed outward from the star to actually essentially take apart the dense core in which it's forming. And you can sort of get a sense of that from this image. So what I didn't tell you about this image is that being from a radio telescope, we're seeing the emission from the gas, but the radio telescope gives you the velocity of the gas as well by the Doppler shift. And that's what the color code is. So red are velocities coming towards us, blue are velocities going away from us. So first thing you see is that the cloud has sort of a red-blue side to it. The cloud is actually rotating like this. But there's a couple regions in here where you'll see many different colors mixed together. So over here, we see blues and greens and yellows and reds all mashed together. Over here too, there's blue areas and red areas and yellow areas and green areas in here. These two regions are the most active regions of star formation right now. So what you're seeing from that is evidence that in quiet regions you get a nice uniform red color. There's sort of a little bit of blue-green, variation. But when you've got lots of stars forming, all of a sudden you're seeing lots and lots of velocities. The cloud's being pushed around by all these outflows. And so we see evidence that this, the velocity of the cloud within these clumps is being influenced by the young stars. They're being shredded from the inside.
Why is the, put that back, why is the blue region moving away from us?
So we don't know for
Ordinarily,
this one.
blue means coming towards you.
Did I get that backwards?
Yes.
I meant yes, blue towards us right away. Sorry.
Okay.
It's the usual convention.
So it's a normal.
Yeah, I flipped it in my head as I was talking. So yeah, so this is, the red's going away, so it's rotating like this. So what's going on here? So young stars, in the big picture, they definitely affect the cloud that they formed out of. When you have massive stars, it's really easy to tell. You blow these bubbles, the massive stars live very short lives, they die supernova, you get an explosion that can shred the cloud from the inside. But even in cases where you don't have the massive stars, when you have just the low mass stars like you do here, they still affect the cloud. They shred these clouds from the inside through the action of their protostellar outflows. And this explains something that we've known for a while, which is that if you look at star-forming regions in different sort of stages of their evolution, you add up how many stars get formed, and you compare it to the amount of gas that was there. And what you find out is that most of the gas doesn't end up in the stars. Star formation is inefficient. And we understand the mechanism for that. The young stars, as soon as the stars start forming, whether it's massive stars or low mass stars, they start shredding their cloud from the inside. And so once you start forming stars, the stars rip apart the cloud and stop the star formation process. It's self-regulating. So that's the sort of progression through star formation. I want to finish with just continuing the story a little bit further along, which is what happens next. So we know that stars are born in groups in these dark clouds. We know that the cloud gets dispersed by the winds, the radiation supernova, the outflows from the stars. So what you have left over at that point is what we call an open cluster. You've got the group of stars still sitting together in the area that they were formed. And a lot of open clusters, certainly the ones we look at, tend to be the biggest and brightest ones. They have a lot of bluish stars in them, and we know those are the most massive ones. We also know the most massive ones don't live very long, so anywhere you see these blue stars, you're looking at a relatively young group of stars. So when you see an open cluster, all you're seeing is the Eagle Nebula, the Orion Nebula, whatever it might be, where somebody hit the fast forward button for a few million years. And that's what an open cluster is. So here's an example. This is M37. Again, you got the lovely blue stars there in the center. Here's another wide field image of two open clusters, Pleiades and the Hyades. And you can actually say something else interesting about open clusters by looking at them like this. So you remember back at the beginning, that cloud was turbulent. It had a lot of chaotic motions. As it forms stars, the stars keep some of that turbulence. They're not moving in an orderly fashion either. So we form the stars blow away the gas and the dust, and we know that removes most of the mass. Well, it turns out there's not enough mass left over then to keep everything together. So all the stars that got formed, everything that was holding the group together by gravity, most of that's gone, so they just keep moving through space in whatever velocity they picked up from that original turbulent cloud and from their interactions with their neighbors. So open clusters over time drift apart. And over the course of a few 100 million years, they essentially disperse completely and become just part of the background stars that we see in the night sky in the Milky Way. And so the density of an open cluster, how tightly clustered it is a rough approximation for how old it is.
Yep.
And so you can look at the Pleiades and the Hyades, and they're at slightly different distances, but they're not that much different. Which of them is younger?
Would be the Pleiades.
Yeah, Pleiades is denser. It hasn't drifted as far apart. So you can tell a little bit something about the age of a cluster by just how dense it is. So there's just a beautiful image of the Pleiades. And what's interesting about the Pleiades, you guys are familiar with the Blue Nebula, the Merope Nebula.
Yeah.
This is not the cloud of gas and dust that the Pleiades formed from. It seems like it should be, but it turns out it's not. It's a chance encounter. if it was the same cloud they formed out of, they would be moving together in space. But if you look at the motions of all these stars, they're very chaotic and turbulent, but as a group, they're sort of moving bulk in one direction. This cloud is moving bulk in a slightly different direction. So it's literally just a chance encounter.
Wow.
Again, over time, clusters disperse. Each star has its own small random velocity left over from the turbulent motions of the cloud, and they disperse and become part of the Milky Way. Now the key is our sun was born in a cluster like this. So our sun had siblings 4.5 billion years ago when it was formed. But we don't know who or what those stars are because it is long ago dispersed. These clusters last a few 100 million years.
I should point out there are a few candidate stars that have the same motion we think may have formed in the same cluster.
Wait, what?
I'm always a little skeptical of that because,
That's why I call them candidates.
yeah, we've orbited the galaxy 20 some odd times since then, and the chance that somebody around us would happen to have a similar velocity is not that unusual, but they're candidates.
Velocity
what's-
and age and yeah.
Yeah, I'm still, candidates is, yes. But the other interesting thing is, we talked about two different styles, essentially, of star formation, the massive stars and the low mass stars. Where did our sun come from? We can actually tell. So when we look at material in our solar system, in fact, there's been some isotopic studies of asteroids, and there's evidence that there were nearby supernova explosions early on in our sun's history. So that means our sun was born in a place more like Orion than like Perseus or Taurus. We had massive stars nearby when we were born. Some of those stars died in supernova explosions. They, spewed out the heavy elements that get formed during the fusion in massive stars and during the supernova explosion, and that essentially polluted our sun's solar nebula, the disk around our sun. So we think our sun formed in an Orion-like environment.
Cool.
So
Now,
again,
can you draw any conclusions, depending on the two types of environments, how rich the planetary system around the star might be? I mean, if it was stripped of gas and dust quickly by maybe nearby stars, would it have a poorer planetary system?
So early on, when that picture of Orion that showed the tadpoles, the proplyds, people were speculating whether or not that would help planet formation and asking what did that have to tell us about how common planets might be. This was before the vast majority of extrasolar planets were discovered. And it turns out that, again, if we assume our solar system is relatively typical, which, that's an assumption, but the gas that the star can hold on to is relatively close in, but it's close enough in to account for most typical planetary systems. So we don't think that planet formation is dramatically
Affected by the...
dramatically affected is probably a good term, by the nearby stars. Now, of course, if you get really close, then you can affect it. But on average, it doesn't dramatically affect planet formation. It affects whether your star has had enough time to grow, and it affects how big the star gets. So again, this is just the big picture of star formation. We start with the dark clouds. We have these two cases where you have low mass stars forming, reflection nebula. You have the high mass case where you have these really bright emission nebulae. And then once all the gas is dispersed by the action of the stars, you get your beautiful open clusters. And then over time, they disperse. So that's it. That is the story of star formation. So hopefully when you go out and you look at these objects, you'll have a little more appreciation for, where they are in their life cycle and what these mean when you see them like that.
Mr. Pleiades.
When you had the that original picture about the yellow nebula when it started, what's the temperature of that? And is it something if you were in a spaceship, would you be able to fly through it, or would you burn up?
So there's a couple of interesting questions there. So if you look at the gas in the massive star forming region, so in Orion, in the Eagle Nebula in Carina, the gas gets heated by the radiation to about 10,000 degrees Kelvin. So it's comparable to the surface of a star. It's really hot, but it's also really, 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 really thin. So there's very few atoms in any given cubic centimeter of the space, so it wouldn't have much of an effect on anything in it at all. It's sort of a technicality that it's that hot. But the particles, the atoms, do have a lot of energy, a lot of heat energy.
That's the Pleiades.
Yes, so this is just that same picture of the Pleiades with the beautiful Merope Nebula.
Now, don't we oscillate in and out of the Orion arm, and why?
Well, so the Orion arm is a much larger structure in our galaxy, right? So this is a spiral arm in our galaxy. And, you know, if a star, so again, within the galaxy, over these hundreds of millions of years timescale, so our sun orbits in about 230 million years. You know, you get tugged from all the nearby stars, you know, groupings, clusters, the lumps of gas, all of that. And so if you get tugged and you start going a little bit, you know, faster up, say in the galaxy, like out of the plane, as you come up, all of a sudden there's a lot of material below you. As some gravity tugs you back down, you sort of fall through. So stars tend to oscillate up and down within the galactic disk, but sort of always staying within the disk.
I mean, that's the whole reason a disk exists to begin with.
Yeah.
Is the material pulls itself together.
Yeah.
Josh, do we know what the period of this oscillation is?
We do, I don't. I don't remember the number off the top of my head.
Yeah, you can look up Lisa Randall, she has an estimate of that.
But because that would put us periodically into denser regions of space, which would periodically put us nearer to younger stars that would go supernova, thus we would have histories of not too far away supernovas, right?
There's a lot of elements in that chain, and even within the disk of the galaxy, star-forming regions, there's a lot of space in between, so we miss the star-forming regions as we dip up and down a lot.
Okay.
Imagine look at M33, you know, in your telescope. You're looking face down. If you look at it, if you take a long exposure, you'll see a bunch of the star-forming
That's
regions.
right. That's right.
You know, if you were to randomly throw a dart at M33, you probably wouldn't hit one.
Right.
So it's still a chance, you know, encounter of going through these, and you have to go through it when it's, you know, really going nuts with star formation as opposed to 100 million years before or 100 million years after, at which point it's just stars.
Okay.
Other questions?
This is very fascinating.
That was awesome.
All right, well, thank you very much.
Josh.
Yeah.
This